All right, so just as a quick recap of what we did in our last lecture, I tried to explain some basic concepts which are important and crucial for this class. And then I give a concrete example about the application of the central limit theorem. So basically, we are going to assume that as our number of i.i.d. random variables n goes large, then we can assume that the average of those n i.i.d. random variables, which we denoted as the xn bar, or equivalently, the sum of those random variables, which we denoted by Sn, would be approximately normally distributed. So with that central limit theorem result, then we can approximate the probability that involves the average or the sum by using the CDF function of the normal distribution. So recall that this is the general form we derived last time. So which replaced the actual numbers with the notations A and B. So they become symbols instead of numbers. And then given the i.i.d.s mean and standard deviation and this number of random variables n, we could actually approximate this probability that the average is between A and B by just using the CDF function, which we denote by big or capitalized phi. Using the CDF function, we can just derive the result. And you can see in the result, it only uses the constants A and B, the mean mu, the standard deviation sigma, and also the number of random variables m. Okay, so in a practical case, we actually use the central limit theorem to consider what we call a sample which contains n i.i.d. So we call them together as one sample, and we denote this xn bar as the sample mean. And we are interested in the distribution of the sample mean, which can be approximated by the normal distribution provided by the central limit theorem. So regarding that, we are going to say more about this today, the relevance between the probability results we will talk about and the relevance to statistics. So in statistics, using this probability formulation, each xi is one observation. We are doing a repeated sampling. And together, x1 to xn form a random sample. Okay, this is something I want to clarify a little bit, because if you see some textbook, especially those in machine learning, sometimes people refer to x1 to xn as n samples, the plural form. So you will see that. And I think this is just ambiguity in the use of terms. So I would say some people say each observation is one sample, but some people say the n observations together is one sample. Okay, so in this class, we are going to follow the classical statistics language and say, oh, x1 to xn is a random sample of size n. That's the language we are going to use. But just bear in mind that in the future, you may see people say x1 to xn are n samples. That's still possible. You will see that. Okay, so then continue from that. So following that, we talk about the gamma distribution. This is more like a review of probability facts, okay? So the gamma distribution is a continuous distribution defined on the non-negative part of the real line, which means that a gamma random variable can only take non-negative real values. And this is the probability density function, PDF, and it integrates to 1. And we talk about two special cases of the gamma distribution. One is the exponential distribution. The other is the chi-square distribution with the degrees of freedom as 1. So we put the degree of freedom in the subscript, and it's 1. So why do we want to introduce this chi-square distribution? Because it's very important, and it's the squared version of the standard normal distribution. So if you know how important standard normal distribution is, then you can know, oh, the chi-square 1 distribution is also equally important. And the reason we want to introduce this is because very soon we are going to talk about the distribution of sample variance. That is, we are going to calculate the variance, define the sample variance based on our sample x1 to xn. And we are interested in knowing what's the distribution of that sample variance, just as we have known the distribution of the sample mean based on the central limit theorem. So in order to do that, we need to introduce the chi-square distribution as a foundation. So that's why we're talking about it here. Okay, this is the definition. Okay, sorry, I should say this is the definition of chi-square 1. And what we want to show is that if we have a standard normal random variable and we square it, then the squared z-square would follow what we defined as the chi-square 1 distribution. How can we prove that? Okay, so last time we gave the idea. So we are going to use the C to derive the CDF of z-square by this definition. And with this definition, once we derive it, we're going to take the derivative against its argument x to obtain the PDF of z-square. And then we're going to show that the PDF is exactly the definition. So if we can match the result from here to here, we're done. So you may wonder why we don't use the Mgf to derive the distribution in this case. The simple reason is that if you recall the properties we taught you about the Mgf, it's about the linear transformation of a random variable, right? We talk about how to derive from, say, the x random variable x Mgf to the Mgf of ax plus b. We told you that, but we never said how to go from x to x squared. So that's why we don't have that tool at hand. But instead, this going from C to derive the CDF of z squared based on what we know about the distribution of z is possible. So we can do that. And that's what we're going to do today to start from here. So given this idea, now let's go to the details. So let's define the give me a second. Let's define the CDF of z squared. Let's call it. So based on our notation convention, we put a random variable as the subscript here for clarity. So I put it here to mean it's the CDF of z squared. And we evaluate it at a non-negative real number x. So by definition, this is the probability that z squared is under x. Okay, and now we're going to make the relevance to z. And given that we know x must be non-negative, we can take its square root. Therefore, this is equivalent to that z is between negative square root of x and positive square root of x, right? This is just by taking the square root. That's what we have. And so because we know z follows standard normal, then we're going to use the standard normal CDF again. And this probability can be written as the CDF of standard normal. We just saw that, the big phi at root x minus big phi at negative root x, right? This is our CDF for z squared by definition. Now let's go to PDF. The density, which I will use small f to denote it. And I still put the random variable z squared in the subscript just for clarity. And we evaluate it at any non-negative real value x. So by definition, it's the CDF derivative. So it's basically d dx. Okay, so we are going to take derivative against x based on this formula. That's what we'll do. And now we are going to do the chain rule. Okay, so by chain rule, so basically I can get a derivative inside it. So it becomes d dx big phi at root x minus d dx big phi at negative this. Okay, so by chain rule, it means that I will first get the derivative of big phi, and that will be the PDF of standard normal, right? Big phi is the CDF. We take its derivative, we get the PDF of standard normal at this root x. And then we will do d dx root x. So let me just quickly give you this explanation as a quick review of the chain rule. It will be big phi prime, which means its derivative, at root x times d dx root x. So this is what I mean by chain rule. And we know this is actually x to the power of 1/2. Then its derivative will be 1/2 times x to the power of -1/2, right? So that's how we'll do. So the result, I'll just give you the result. It will be basically, this is the lowercase phi. Small phi means the PDF of standard normal. I'll write it here, is the PDF of standard normal. So the lowercase for the PDF, the uppercase for the CDF. So I evaluated at this, okay? Based on chain rule, I will get this. This will be the derivative of the first term. And for the derivative of the second term, I will just write it down. I'll leave it for your verification. Okay, so this is what I have. Basically, because of this negative sign, it will go out and I get a positive sign here. Okay, and now for the PDF of standard normal, this is something everybody should know, right? So this is the most important PDF. If I want to name one, it should be the one that you should know. So basically, if we evaluate it at x, and the x is any real number, it takes this form, 1/√2 pi exponential to the power -x²/2. So I hope everybody should remember this form, because this is something we'll use a lot, not just here, but later when you learn some machine learning, when you see people say Gaussian kernel, you are going to see this form again and again, everywhere. Okay, so and we know its shape, right? The shape is just a bell shape, concentrated around 0 with symmetric tails to the two ends. And what we also know is that, just a quick review, so between say -1.96 to +1.96, the probability, the area in the middle is about 0.95. So these are the basic facts about the standard normal distribution. So a question in the chat box, can you repeat it? I am not able to see what's next to the 2. What do you mean the 2? There are multiple 2's here. 2 pi, okay. Yeah, this is so pi is involved in this. There's a constant here. Okay. So, right, so this is the normal distribution. Standard normal distribution, we will use constantly. So the reason I write down this formula is because we're going to use it here. Okay, so we can simplify the PDF to get a final form we need. So now I'm going to evaluate this phi, small phi, at this root x. So I'll just write it down. It will be actually 1/√2 pi exponential to the x/2, right? Because I'm going to evaluate at root x, whose square becomes x. So this is the thing, right? I hope everybody can know, given this form, how do we evaluate it at root x? This is a basic math technique. You need to do the replacement, right? You don't confuse this x with this x. They're not the same thing. This x is just a placeholder in the function. So as I said, I can replace it by t, and it's still the same function. So I can write this. So it doesn't have to be x. It's just a placeholder, the symbol. So that's why when we plug in this root x here, we will get x. Okay, so this is something I hope everybody should stay on the same page. Otherwise, any future discussion will become very difficult, right? How do we interpret a function? Yeah, so don't just memorize this as x. X is just a placeholder. So that's why I can even make it even more abstract. let me just write one more line here. I can even write it this way. I just put a dot here, and I can write dot square over 2. I can even write it this way. So the symbol doesn't matter. Okay, so then coming to here, this is what I get. And I'll just write the rest down without explanation. Okay. Okay, that's what I have. So now you see, we can combine these two terms, right? Because they are identical, right? They're identical, I just add them up, which means it's equal to this term times 2. So I get this 2 in the denominator away. Then what do I have? Let's see. I would have a root 2 pi times root x, okay, exponential negative x over 2. That's what I have. And then let's try to match this result with this result. Okay, so this is something I intentionally didn't talk about last time. It's about the gamma function. So for gamma function, we have several interesting facts about it. So I would say the most important fact about the gamma function, probably I put it here as a separate note. So about this gamma function called gamma. And I think this is the reason why people call that gamma distribution, because it involves the gamma function. A very important fact is that we evaluated at x, say x positive, non-negative, then gamma x plus 1 has this property equals to gamma x times gamma x. And this can be obtained by the chain rule based on the definition of the gamma function here. Okay, it's defined as an integration gamma function, and based on not chain rule, sorry, my bad. Based on the integration by parts, you can obtain this interesting result. Gamma x plus 1 equals x times gamma x. And another important property about the gamma function is that when you evaluate it at 1/2, the result is root pi. Okay, now using this result, let's go back to the PDF of the chi-square 1 density. So basically, you see, if I write it here, root 2 is in the denominator times gamma 1/2 is root pi. And this x to the negative 1/2 can also come down as root x in the denominator. And what I'm left with is x to the e to the x over 2. Okay, now you see this and this are exactly the same. So we match the PDF function of this z square with the PDF function of the chi-square 1. Do we see that? It's exactly the same thing. Okay, so because this is the PDF of chi-square 1. Okay, so finally, the conclusion is that z square follows chi-square 1. So we just did a proof here. The proof is that we start from a standard normal random variable, and we prove that its square follows chi-square 1 distribution. That's what we did. And the proof is based on that if we can match the PDF, we can show the PDF function of z square is the PDF function of the chi-square 1 we defined, then we say the random variable z square follows chi-square 1. Okay, do we have questions about this? Okay, so if not, then we will continue. And by continuing, we will introduce another special case of gamma distribution. Okay, so continuing from here, we said that in the gamma alpha beta, when alpha is 1/2, beta is 2, this is called the chi-square 1 distribution. Okay, So let me say that special case 3 of this gamma distribution. Let's say now we set alpha equals to n over 2 and beta as 2. And in this case, we call this distribution as chi-square with n degrees of freedom distribution. So you see, basically, we're just generalize alpha from 1/2 to n over 2. So when it, and this n, this numerator in this alpha ratio, so the denominator is kept as 2, and the numerator is the degree of freedom of the chi-square distribution. So this is what we define, okay? So another thing I want to say is that recall you did this in your homework, the Mgf function of chi-square, Mgf function of gamma distribution. So recall that the Mgf of gamma alpha beta, based on our definition for density function as this, is I just call mt, evaluate t. So know that here I'm not putting a subscript x, but because I'm not saying a particular random variable x. So that's why I dropped that notation, because we're not specifying a random variable here. But this is actually, we derived it as 1 minus beta t to the power negative alpha. So we did this in our homework. That's the Mgf. So with this, then what I want to say is that just by putting in the special cases of alpha and beta, we can say the Mgf of chi-square n, chi-square distribution with n degrees of freedom is mt equals 1 minus 2t to the power negative n over 2. I didn't do anything special, just put in alpha and beta. And that's the Mgf of xm. So why do I need to do this? The reason is that this gives me a foundation to prove our theorem 2. So theorem 1 is what we just did. For z standard normal, z squared is chi-square 1. Now for theorem 2, we are going to show that if you have n i.i.d. standard normal random variables, so you now have n of them, not just one of them, then what we will show is that the sum of their squares, sum of zi squared, I from 1 to n, would follow chi-square distribution with n degrees of freedom. So you can consider this as a generalization of theorem 1. In theorem 1, n equals 1. So it's only z1, and z1 squared is chi-square 1. We did that. Now we are saying with n i.i.d., we square each and we take the sum. The sum is chi-square with n degrees of freedom. So the magical thing here is that the degrees of freedom is just equal to the number of random variables we have here. Okay, so to prove this, we are going to use the Mgf. The reason is that we already know each zi squared is chi-square 1. So we know their Mgf from here. And then we just need to show the Mgf of their sum is this. Okay, so the proof is to use Mgf. So based on theorem 1, we have zi squared, each zi squared follows chi-square 1. So I hope everybody can try to follow me and see how we did a formal proof. I know that not everyone has this experience before. It's in particular with our stats courses probably. So, but I hope that people can try to follow the logic and see, oh, when I need to claim something, I need to provide the evidence. So every statement, the proof must go from somewhere we consider as knowledge or the condition, go to a statement, and we go from there. So every step needs to be justified. So based on theorem 1, we have this. Okay, and then we know that these things are all independent. Okay, so because of this, so the Mgf of zi squared is, I will just call this mzi squared. Now I put it in a subscript to mean, oh, we're talking about this random variables Mgf. Evaluate t based on our knowledge, based on this recall, right? So this is we just did. So it's actually equal to 1 minus 2t and chi-square 1. So n equals 1, negative 1 over 2, based on what we just recalled. So now, because z1 squared to zn squared are independent, and this independence is from the fact that z1 to zn are independent. Therefore, we square each, and their squares are still independent. And this can be understood from the definition of independence. I'm talking about that again. Independence means that whatever value z1 takes, the distribution of z2 to zn will not be affected. So therefore, putting it in the square form, no matter what value z1 squared takes, then the distribution of z2 to zn will not be affected. So the distribution of z2 squared to zn squared will not be affected, right? So by the definition, we can carry over the independence. The reason why n is 1 is because we are talking about chi-square 1. So we have this zi squared following chi-square 1 from theorem 1. Does that make sense? This is what we just proved. And I'm just saying that this is the form of the Mgf for x and not x, for chi-square n squared. So with this, then let me just write one more step. The Mgf of chi-square 1 squared is the Mgf of chi-square 1 is, that's it. That's the thing I'm using. Is zi gamma function? No, zi's are standard normal. Why are we thinking about zi as gamma? So here we are talking about this theorem 2, and this theorem 2 has its own condition. And the gamma part is just some facts to review. Zi squared, it is gamma because we said zi squared is chi-square 1 from theorem 1. And we also said chi-square 1 is a special case of gamma, right? Chi-square 1 is a special case of gamma with alpha equals 1/2, beta equals 2. Does that make sense? Okay, so if there are questions, please raise your hand and let's try to clarify all the questions before we proceed. Okay, so maybe let me try to clarify things again. So let me go from more general to more specific. Okay, chi-square alpha beta is a general class of distributions. And when we set its alpha parameter to n over 2, beta to 2, we are at a special case of chi-square with n degrees of freedom distribution. And furthermore, when we set n equals to 1, we have chi-square 1 distribution. So in other words, chi-square 1 is the most special one among the three. Gamma is the most general one, and chi-square n a little more specific, and chi-square 1 most specific. And in theorem 1, we just showed for a standard normal random variable z, its square is chi-square 1. And here we are going to show that for n random variable standard normal, we square each and we take the sum, and the sum will follow chi-square n. And we are going to prove that. So we are actually in the middle of the proof. Okay, so if there are no more questions, let's continue. Because they are independent, recall that we have that independence property for our Mgf, right? We did that before. So we have for the sum, okay, for the sum zi square I from 1 to n at t. Based on the property we learned before, we can write this as the product z1 square at t multiply up to zn square at t. Do people still remember this? When are independent, we can factorize the Mgf. Okay, and I'm going to introduce this notation because I know from my previous years of teaching this class, not everybody saw this before. This means the product. We let I go from 1 to m, and m zi square t. So just like this this big sigma means summation, this big pi means product. Okay, and so from here, then let's put in this. So because for each zi square, its Mgf is this form. So in other words, we have n copies of this multiplied, right? So that will give me this multiplied for n times. So it will be 1 minus 2t, this thing to the power n. That's multiplied for n times. Now we know how to simplify this, right? A power raised to another power is equal to the space raised to the product of the two powers. So it's 1 minus 2t to the power negative n over 2. And we recognize this is the Mgf of chi-square n, which is the Mgf of chi-square n. So then we have the result. So so summation I from 1 to m zi square follows chi-square n. So I hope this can show you again that Mgf is a very useful tool for deriving the distribution of a random variable. With this tool, we can simplify a lot of arguments about why this follows that, because the Mgf just provides the tool we can use. Okay. Are people okay with this proof? Okay, and also just to make this clarification again, thank you, Brandon. We can say this is gamma with alpha as n over 2, beta as 2, right? That's the gamma specification, and this is the definition of chi-square n. Okay, so now we are going to do a corollary. You know, in mathematics, when we say a corollary, it's a straightforward result from the theorem, which doesn't require a complicated proof. Okay, so the corollary from theorem 2 says that now let the i.i.d.s go from standard normal to general normal. Let x1 to xm be i.i.d. normally distributed with mean mu variance sigma square. And we're going to say that the sum I from 1 to n of xi minus mu divided by sigma, this ratio squares, will follow chi-square n. Okay, so this result should be obvious to everybody. Let's think about it, right? Why would this hold? Based on theorem 2, this result should be straightforward. Can someone volunteer to give me your answer why this would hold? I would say just one line to prove it. Like maybe Ran, would you like to give it a try?
Yeah, so the normalized form xi minus mu divided by sigma is has the distribution of normal 0, 1. So the sum of its squared is just use the theorem 2, we can get this.
Exactly.
Follow the chi-square. Yeah, the m.
Yeah, thank you. Thank you. Yeah, exactly. Yeah, she said it perfectly. So the reason is that, thank you, Brandon, because since we have this condition, right? We would have, so since xi follows normal this, so we would have the standardized form follows standard normal, right? Then we apply theorem 2. Yeah, theorem 2. So when we say write theorem, a lot of people just write in short as THM for short. Okay, so that's theorem 2. And for theorem 3, which is also going to be an application of the Mgf independence property. Okay, so let's say that we have two random variables. Let x follows chi-square with degrees of freedom as m. Y follows chi-square with degrees of freedom as m. And x and y are independent. So we have two random variables that are both chi-square distributed with different degrees of freedom, but they're independent. Then what we can have is that x plus y, their sum would follow another chi-square distribution with the degrees of freedom as m plus n. So this is a nice property about chi-square random variables, independent chi-square random variables. That means if you take the sum of the random variables, then the sum would still follow a chi-square distribution, but the degrees of freedom would add up. Okay, to show this, we are again going to use the Mgf. So we are going to use this general form of chi-square n, 1 minus 2t to the power negative n over 2, and n is the degrees of freedom. Okay, so the Mgf of x is mx at t equals to 1 minus 2t to the power degree of freedom n over 2. And similarly, the Mgf of y is myt equals 1 minus 2t to the power of degree of freedom, which is n over 2. Now we're going to use independence. Because x and y are independent. Okay, we would have the Mgf of x plus y is mx plus y at t. Again, use the property that when we take the sum and they're independent, then the Mgf can be factorized by the products of their individual Mgfs. Mxt times myt. Okay, and put them in. So basically, they share the same base. And we know that when we multiply two power terms with the same base, we just add up their powers. So that's 1 minus 2t to the power negative m plus n over 2, right? I combine the power. So you see, this is actually, we can recognize this is the Mgf of chi-square with degrees of freedom as m plus n. So we conclude that x plus y follows chi-square with m plus n as the degrees of freedom. Okay, So that concludes our discussion about the chi-square distribution. And it has very interesting properties. That is, when you sum up independent chi-square, the sum would still follow chi-square with the degrees of freedom as the sum of individual chi-squares degrees of freedom. And also, this result will remind me of another result about normal random variables. So recall that if X follows normal distribution with mean mu1, variance sigma 1 squared, and Y follows normal distribution with mean mu2, variance sigma 2 squared, and X and Y are independent, okay? So this is the result I'm going to write down, but I think everybody should be able to verify yourself using the Mgf. Okay, so what we have is that then X plus Y will stay as a normal variable with mean as mu1 plus mu2 and variance as sigma 1 squared plus sigma 2 squared. That's the first result. And the second result is that X minus Y, if I take their difference, it will still be normal as well. And the mean would be mu1 minus mu2, and the variance would be sigma 1 squared plus sigma 2 squared. A common mistake is that people will put minus here. But if you think about it a little more carefully, you can know why minus couldn't be correct. Because if your sigma 2 squared is bigger than sigma 1 squared, if you have minus here, the difference will be negative. And we know that the variance could never be negative, right? That's a very straightforward counter proof to see why this couldn't be minus. So this is what we have. And intuitively, what this says is that given the uncertainty of X, this variance measures the degree of uncertainty that X is from mu1, squared difference about the uncertainty. And given this amount of uncertainty for X and this amount of uncertainty for Y, so no matter you take their difference or their sum, the uncertainty would always accumulate, right? They instead of counteract. So that's the thing we should bear in mind. So that's why you have this add up for the variance. And now let me give you the more general form. So for any a real value A and real value B, if I do AX plus BY, okay, in this general form, then the mean would be A times mu1 plus B times mu2. You put this combination into the mean, and the variance would be A squared sigma 1 squared plus B squared sigma 2 squared. So this is the general form. And these two are just special cases of this, like A is 1, B is 1, or negative 1. So to prove this, you can use Mgf, and I will leave this to you. Okay, so try to prove them by Mgf. So for the general case, you are going to use the linear transformation property of the Mgf as well as the independence property about the Mgf, and you'll be there. Okay. So that's all I want to say. Any questions before we move on to our next topic? All right, so if there are no more questions, let's continue. So the next topic is something very interesting about an important property of Gaussian random variables. So this new topic, let me try to say that this is something important properties of normal random variables. So all the following will be based on normal random variables. And now I'm going to start my numbering of the theorem, restart the numbering, because this is a new topic. So now here we start with i.i.d. random variables from normal distribution with mean mu, variance sigma square. And we define its average by x and bar. So know that n means the number of random variables here. So what we call the sample size, right? So that's why we carry it here. It's a meaningful parameter. And define this as 1 over n of the summation of xi. Okay, now we're going to show a very interesting property. This property doesn't hold in general, but it does for normal random variables. So we're going to show that xn bar and whatever I, xi minus xn bar are independent. So this statement looks counterintuitive at the first glance because xn bar is involved in both terms. Then how can the two terms be independent? That might be a question you would wonder. So we said that independence means whatever value this term takes, this term will have an unaffected distribution. So the distribution of this one has nothing to do with the value of this one. But this is in the term, right? So xn bar is in the term. So how can it not be affected? This is actually this holds for normal distribution because of a very important property of our normal distribution. That I would say the property, the nature of this property is that basically the normal distribution is very symmetric, and also it can only be specified by just the mean and also the standard deviation around the mean. So the reason why these two can be independent is sort of, I would say intuitively, can be interpreted that here, whatever mean I take, I can shift my distribution, but the distribution of this difference will not be affected. Okay, so that's the intuition, but this intuition doesn't mean we can prove it. To prove it, we will need some tool, and the tool we will use is the Mgf. So here, to prove this theorem, the tool we're going to use is something I mentioned last time. So we're going to show that the joint Mgf of these two variables together, xn bar and xi minus xn bar, can be factorized into the Mgf of xn bar and the Mgf of xi minus xn bar. Okay, so by factorize, we mean one is a product. This is the product of those two. So recall, this is based on the fact that if we have the Mgf of two random variables x and y evaluated at s and t, two real numbers, if we can write this as this factorization, this is what I mean by factorization, then this is equivalent to say that x and y are independent. This is something I mentioned last time, so I'm doing this review here again. Now, what's remaining for us is to derive the Mgf, joint Mgf of xn bar and xi minus xn bar. Okay, that's the task, and we're going to proceed from here. So, based on the definition, of joint Mgf, we would have the joint Mgf of xn bar and xi minus xn bar evaluated. This must be a bivariate function at s and t. be defined as the expectation of exponential function s times the first random variable, that's xn bar, plus t times the second random variable, that's xi minus xn bar. This is t, okay? So the question is, how do we open this up? How do we compute this? So we know that xn bar is based on x1 to xn, the average. So we need to use that. So in order to simplify the power here, let's first do, note that the power needs to be simplified. We write it here, s times xn bar plus t times xi minus xn bar. I first try to combine the similar terms. The similar term here is xn bar. So I would have s minus t times xn bar plus t times xi. Okay, that's what I have. Now, what I want to do is that because in my original condition of this theorem, what our i.i.d.s are x1 to xn. So what I want to use is the Mgf of normal distribution, right? And in order to use this i.i.d. property, I need to express this expression in terms of x1 to xn. Then I can use the x1 to xn's Mgf to go from there. So I just put the definition of xn bar here, 1 over n sum of xi. Okay, and finally plus t times xi. So now this expression is just about x1 to xn. And then you can see what amount x1 to xn, what term is special in this expression? Can you tell me? So from x1, x2 to xn, which term is special in this expression and should be treated differently? If you consider each xi's coefficient, which one has a different coefficient? So Brandon, I think you know the answer, right? Do you want to give it a try?
Whichever one the I is.
Yeah. So xi, the one with the I as the index, this one appears twice, right? Once in the sum, once individually. So it has a different coefficient from the rest. So therefore, you see, I can write it as, I can take this term out and put its coefficient into a sum. So it has a coefficient s minus t over n from the first term, and it has a coefficient t from the second term. Put them together, times xi. Okay, that's its coefficient. And for the remaining ones, their coefficients are the same. So plus s minus t over m times the remaining. So for the remaining, I'll just call them j, whatever j doesn't equal I, and I take their sum. So this is also a common expression you will see. So when people want to take the sum, but want to exclude one index, they can just write whatever j is not equal to I, and then I put in the sum. So xi is excluded from the sum. Okay, so that's how we're going to express it, right? So we are putting this expression in terms of i.i.d.s. So going to the joint Mgf, we want to do this one. Okay, so now, we put those inside here, okay? So it becomes exponential to s minus t over m plus t times xi plus s minus t over n, j doesn't equal to I xj. So this is what we have. Okay, and then independence comes into play. we're going to use the fact that x1 to xn are i.i.d. to factorize this thing. i.i.d. independent. Okay, so in other words, this is basically, if I just write it one more step, this is basically, okay, if I want to write it one more step, then I will use this condition next. So I'm going to say that just to help people stay on the same page, we can write this as a product inside expectation. Okay, s minus t over m plus t xi. This one times the product j doesn't equal to I, exponential to the power s minus t over n times xj. Okay, so do people follow this step? From here to here, I'm just using the fact that sum in the power can be written as product. Okay, so now I'm going to use independence. x1 to xn i.i.d. Independence means that I can write expectation of product to as the product of expectations. So this can be written as expectation of exponential s minus t over m plus t. This times product. Now I put the expectation inside the product. Right? This is what I would have. And then we know this can be used, this can be based on the Mgf, right? Mgf of xi and Mgf of each xj. So this is basically the Mgf of xi by definition at s minus t over m plus t. And for the remaining, is the Mgf of xj evaluated at s minus t over m. And I think you have seen this in your homework for more than once, multiple times, you should have. Okay, are people with me? Okay, sounds good. Then now we are going to use the Mgf of each xi and xj from what our knowledge. So recall that for xi follows normal distribution with mean mu variance sigma square. This is the condition of our theorem. The Mgf is, this is we did a few lectures back, exponential to the mu t times, sorry, plus, I can just write plus sigma square t square over 2. This is the Mgf of the normal distribution. Okay, so the t argument appears here as the linear term, appears here as the square term. Okay, and then what we will do is to use that. So with this, so this joined Mgf, we go to this derivation again. S and t. This would become exponential mu times s minus t over m plus t. Okay, plus sigma squared over 2 times s minus t over m plus t squared. So see this connection? I'm just putting this term as the argument in the Mgf. So it will appear as itself here and as a square term here. Okay, and then continue. For j doesn't equal to I, that means we have this is a product of n minus 1 times. Okay, so for here, we are going to put this as the argument of the Mgf. So it's mu times s minus t over m plus sigma squared over 2 s minus t over n squared. The same reason. Okay, and as I said, here you see in this, inside this product, J is gone, right? There's no J anymore. It's basically the same term multiplied by n minus 1 times. This is what I want to say. So that's the same term multiplied by n minus 1 times. Okay, so we're going to simplify that. In other words, this is equal to, I'll just write it here. It's equal to this e to the mu s minus t over m plus sigma squared over 2 s minus t over n squared. This thing to the power n. And again, you guys should know that this is equal to n multiplies with the power, right? So we do the multiplication that. So then we will simplify this further. And, oh, sorry, n minus 1, my bad. N minus 1. Okay, so that will be it. And the n minus 1 would go inside. So I think what I want to do is that probably I will just go to this line. Yeah, put them together. So basically, I will have a very, very long term in the power of the exponential. So I'll put e here, and I have a long power to write down. So it's a mu s minus t over m plus t, okay, plus sigma squared over 2 s minus t over m plus t squared. And finally, I want to have the terms from here. So I would have, okay, this is what I would have. So it will be mu times s minus t over n times n minus 1. So the n minus 1 is from the power here. And finally, sigma squared over 2 s minus t over n squared times n minus 1. Okay, this is the long term. I need simplification. All right, so what I want to show is that I want to show this can be factorized. So this xi minus xm bar st, I want to show that this is equal to the Mgf of xm bar at s times the Mgf of xi minus xm bar at t. So I need to make this as my final goal. So now I have the left-hand side in this form already. So to make it easier for this proof, this is a technique it's always used, right? So we can go from the right-hand side, write down what's this, and then whether their product is equal to that, and we're done. So we try to go from both directions and match them. All right. So now derive mxm bar at s to see what is this. So to do this, we are going to use the fact about the distribution of xm bar. Recall that xm bar as the average of those i.i.d. normal would follow normal distribution of mu variance sigma squared over m, right? Recall that. This is something we did before, and now we're going to use this fact. So put us into this general form of the normal distribution. You see, the mean is here, the coefficient of t, and the variance is the coefficient of t squared with this 2 in the denominator. So basically, with this, and now the argument is changed from t to s, this should be equal to e to the mu times s, okay, plus the variance is sigma squared over n, okay? n is here, and we also have 2 from the formula s squared. That's what we have. Okay, this is the Mgf of x n bar. Okay, how about the Mgf of xi minus xn bar? That's a little complicated. So for that, we should write down what's this. So xi minus xn bar. Please note that xi and xn bar are not independent. Okay, so we cannot write, what I want to say is that in this case, you cannot simply write it based on any independence. So I should say that note, probably I should say this first, that xi and xn bar are not independent. The reason is that xn bar involves xi. So in this case, whenever you change xi, xn bar will change accordingly, right? So they're not independent. But you can still derive its distribution. But we can derive the distribution of xi minus xn bar. So basically, we'll go to the definition of xn bar again, which is 1 over n summation of xi. Okay, so again, we're facing this case. We need to decide which one has a special coefficient. And based on previous Brandon's answer, and this is similar here, it's just xi. So xi itself will have a coefficient 1 from the first term and the minus 1 over n from the second term. So that's special. And other things will stay in the sum, minus 1 over n. J doesn't equal to I xj. Okay, same argument. Now we are just going to derive what's its distribution. Again, it's just a linear combination of i.i.d. normal random variables. So that's why we know it should follow a normal distribution. Okay, so we know this must follow some normal distribution. But what's left for us is to fill in the expectation and the variance. So the expectation of xi minus xn bar is actually pretty straightforward. For this one, we actually know it, okay? So it's actually expectation of xi minus expectation of xn bar. And actually both are mu. So it's mu minus mu is 0. So we put 0 here. We know the normal distribution should be mean 0. And for the variance, this one is a complicated, so we will use this expression here. So it will be the variance of 1 minus 1 over n xi minus 1 over n summation j doesn't equal to I xj. Because these are all independent, so I can write the variance of their sum as the sum of their variances. Okay, so this will be equal to 1 minus 1 over n. When the coefficient comes out, it will be squared variance of xi. Okay, plus other things will be squared. 1 over n squared. Summation j doesn't equal to I. Variance of xj. Okay, we're here. And now we're going to use that for each xi and xj, the variance, they are all sigma squared. So it becomes 1 minus 1 over n squared, sigma squared, plus 1 over n squared. And this sigma squared has been added up for n minus 1 times. Okay, so finally, we're almost there. So let's just simplify this. It's actually n squared. This one is n minus 1 squared in the numerator, okay? Plus, from the second term, n squared. And what we have is n minus 1. Together, sigma squared. I'm doing the algebra here. And then finally, can we combine these two things? So it's just the numerator, right? And what do we have? N squared. So we'll open this up. It's actually n squared minus 2m plus 1 plus n minus 1. Okay, sigma squared. So just one more step. So here, negative 2n and n leaves me negative n. 1, negative 1 canceled. So it's n squared minus n sigma squared. Finally, I remove n from both numerator and denominator. I left n minus 1 sigma squared. All right, so finally, this is the variance of xi minus xn bar. And I put this result into the new normal distribution. N minus 1, okay? So these two things are just to derive this normal distribution. All right, so finally, this is our mu. This is our new variance. Oh, sorry, I forgot square. Here. So now let's look at the Mgf using the normal distribution's Mgf. So the Mgf of xi minus xn bar at t would be equal to exponential mu is 0. So mu times t will be 0. Okay, and what I'm left with is the variance. So it's be n minus 1 sigma squared over n times 2 times t squared. Okay, so we're just using that formula. So are people with me? So for the right-hand side, now we have this term and this term. Both are derived using the Mgf of the normal distribution. Okay, sounds good. So yeah, I like it when you give me some feedback, so I know whether you are still following. All right. So, but if you have any questions, this is a good place to pause, maybe for 10 seconds, and wait for questions. All right. So if not, then we're almost there. So finally, it's left to show that this equals to this multiplies to this. Okay. So in other words, we are left to show that for this, I call it star. Star is equivalent to the powers are matched. So mu times s minus t over n plus t plus sigma squared over 2 s minus t over n plus t squared plus mu s minus t over n times n minus 1 plus sigma squared over 2 s minus t n squared times n minus 1. Okay, we're left to show that this is equal to mu times s plus sigma squared s squared over 2n, that's from here, plus n minus 1 sigma squared t squared over 2n. Okay, so we are left to show that this line is equal to this line. And what's left for us is simply algebra. Okay, can you move the paper up? What formula are you using for Mgf? The formula I'm using is just this formula. For normal distribution, its Mgf is this. And we showed that xi minus xn bar is normal distribution, has normal distribution with mean as 0. So the mu is 0, and this sigma squared becomes this term. So I'm just putting this mu as 0, sigma squared as this term into this formula. That's how I got the Mgf of this. Okay, so Okay, so then what's left is the algebra, right? So we can see that the most simple, what I would do is that I will try to, so you see this on the right hand side, mu s is the only term that involves mu. So what I will do is that I will take all the terms involving mu from the first line, try to combine them, see if after the combination I got s. Okay, then I'm done with this mu term. And for this term, this is the only term involving s squared. I will try to combine whatever term left here involving s squared. See if it matches this one. And finally, this is the only term on the right-hand side on the bottom line that has t squared. So I will try to grab all the remaining terms after I match those two, the remaining terms to see if they can be combined into this term. Okay, so that's just the idea of doing this algebra to prove this. But since we are actually out of time here, so I will try to leave this verification to you. Try to do this as a take-home exercise, and we'll come back. I'll just try to do this quickly in the next Monday lecture. Okay, but try to stay clear and don't be overwhelmed by the details, especially the algebra in the proof. What we really try to show is this independence, okay? And we use the technique that the joint Mgf can be factorized. So that's the key. And everything else is just algebra. Okay, and we use the Mgf form of the normal distribution for multiple times. So from this class, you can see that whatever we learned in the past lectures are not useless. We kept using them. So that's why it's very important that you stay on track and don't get lost, right? Because otherwise, if we're using the previous knowledge, then we assume you already know. So I would say that you can see more and more why we want to learn the Mgf in the beginning, because we're using this as a technique. Okay, so hopefully that makes sense, and I'll see you next Monday. Bye.
Hi, Professor.
Yeah.
For the theorem 3 we talk about today, I'm not sure the signal there is x or what.
What do you mean by signal?
Theorem.
We have two random variables.
Yeah, x
and y.
plus y.
Yeah.
So
Now it's x. Yeah.
So x here is how to say, like x plus y, and there's another x, right? So this is x or the
One is chi-square. So I write the chi-square is the distribution.
Okay.
So we only have one x, one y. We know x follows chi-square m, y follows chi-square n. And we try to say x plus y follows chi-square m plus n. That's what we're saying here.
Okay, thank you.
Okay.
Hi.
Yeah.
What's the motivation of the last theorem?
You mean the reason, or we are just trying to show this is an interesting result of this Gaussian normal distribution random variable. So using this result, next time we're going to show that a direct implication of this result is that the sample mean xn bar and the sample variance we calculate from xn xn, they are independent. That's a very important property we're going to. Yeah.
So does this theorem has name?
I don't think so.
Okay.
Yeah.
Thank you.
Okay. Thank you.